Does that work? Well, okay. All right. Yeah. So anyway, I want to talk about Dehn surgery eventually, and because some of the most dramatic applications of the Heegard-Floer homology theory have been to Dehn surgery. So I wanted to talk about Dehn surgery. In order to set that in the right context, I have to say something about the structure of three manifolds. So today I'll just start talking about three manifolds and just make some general remarks about their structure, because eventually we're going to be talking about so-called exceptional Dehn surgeries, and I guess we have to know what sort of exceptional means. So let me just begin by saying that, by breaking the chalk. All right, okay. All right. All right. So, there we go. That's better. So I'm going to talk about three manifolds in Dehn surgery. Huh? Okay. So the main task, remember, of geometric topology is to classify, let's say, closed, connected N manifolds, up to homeomorphism, let's say. Okay, so that's the goal. And so how do three manifolds fit into this general picture? Well, let's remind ourselves that, the low-dimensional cases are kind of easy. Ron used the classification of zero manifolds in his talk this morning. There's only one. You might wonder about the empty manifold, but I think we decided somewhere recently that the empty set is not connected. So that's that. So that's okay, right? And then so there's only one manifold, and of course, again, let me just remind you that when n is 2, things become slightly more interesting, but still very nice. I mean, every 2 manifold is homeomorphic to exactly one of, well, and then you just have the connected sum of various copies of the torus, let's say k, okay, greater than or equal to 0. So that includes the 2 sphere, k equals 0. And then, or a connected sum of copies of the projective plane. So that's a good start. So this is a good opportunity to remind you then of the definition of connected sum. This works in any dimension. If you've got two n manifolds, so M1 and M2 n manifolds, then I take a couple of n disks, di in mi, remove their interiors and glue the resulting manifolds together by some homeomorphism. So this is M1 connected sum M2, and H is a homeomorphism from boundary D1 to boundary D2. And again, remember this is well defined. This is well defined in sort of two. Probably the easiest category to work with for this is the PL category. So it's well defined for PL manifolds, or for oriented PL manifolds. And in the oriented category, of course, you have to take H to be orientation reversing. Then so that's the connected sum, and as I said, the two manifolds, of course, are just very naturally classified in terms of connected sums. And of course, already with this definition, you have that the connected sum with Sn is M, and you have the notion of primality. So M is prime if and only if M homeomorphic to M1 connected sum M2 implies that M1 or M2 is homeomorphic. So in dimension 2, there are only two prime manifolds, the torus and the projective plane, and everything is a sum of prime manifolds. Okay, so that's dimension 2. Again, in higher dimensions, we can safely ignore those because the problem is impossible, right? Manifolds are logically sort of unclassifiable. This is a famous result of Markov in the 50s because of problems with fundamental groups. And so that's why Ron, of course, decided to stick to simply connected 4 manifolds. So, but you can't hope to classify manifolds of dimension 4 or greater. So that leaves dimension 3, and dimension 3 does occupy an interesting sort of special sort of place in this hierarchy there, in the sense that apparently they are not logically unclassifiable. In fact, they've been proved possibly to be classifiable as we speak. But I'm not going to say anything about that issue. I'll describe what the geometrization conjecture is, and if it's been proved, that's fine, and if it hasn't, that's also fine. So we're not going to don't expect an opinion on that. What? Well, I don't know. They're both good. Yeah. Yeah. So I should. So what is known in dimension 3? Yeah, I should say, of course, that the classification of 2 manifolds. In some sense, this was probably known to Möbius. It wasn't really proved until it was probably around about 1925, when Rado proved that 2 manifolds were triangulable, and so what's known in dimension 3? So again, let me just a classical theorem due to Moïse in 1954 that at least 3 manifolds are triangulable. So every 3 manifold has a triangulation, and the triangulation is unique up to subdivision. So there's so that's the Hauptvermutung, the triangulation and the Hauptvermutung for 3 manifolds. So every 3 manifold does have a unique PL structure, and equivalently a smooth structure. Another important classical theorem about there's still room. Another important classical theorem about 3 manifolds. Actually, from now on, let me assume, just for simplicity, that I'll assume that all my three manifolds from now on are orientable. Okay, so I'll make this blanket assumption throughout. And of course, at this point, they're all closed as well. So they're all compact without boundary, and I'll assume they're orientable, just for the simplicity of the statements, because it doesn't make much difference, but you just have to say slightly more complicated things. So, and then there's another classical theorem going back to the notion of connected sum here. It's a classical theorem of Kneser, 1929, that every 3 manifold is actually a connected sum of prime 3 manifolds. And the prime summands are unique. Unique up to homeomorphism. So, I don't know. You probably shouldn't think of S3 as being prime. S3 is the empty connected sum or something. I don't know. Anyway. So maybe, anyway. Oh yeah, so and then there's a slightly, Kneser actually works in terms of a slightly closely related idea of irreducibility. So one says that M is irreducible. So again, I'll use this a lot. M is irreducible if every 2 sphere in M bounds a 3-ball in M. So if every S2 bounds a D3 in M. And irreducible is almost equivalent to being prime. The only, so M is prime. It's easy to, M is prime if and only if M is irreducible or S2 cross S1. So S2 cross S1 is clearly not irreducible, but it is prime. And a famous theorem of Alexander is that S3 is irreducible. This is a school, right? Summer school, so you get homework. So here you are, right? So there's, got to prove that, oh, not this one, don't prove it, that's hard, but this, you can prove that M is prime if and only if it's irreducible or S1 cross S2. Yeah, so I'll be assigning homework throughout the lecture. Okay, now, did we get a grader? All right. Well, okay, so these are rather basic. These are sort of rather basic theorems about 3 manifolds, and let me just again remind you, though, it was known again, certainly in the time of Möbius, that in dimension 2, 2 manifolds. I've got some actually have geometric structure. So let me discuss that a little bit. So I don't have many transparencies, but I was going to just at least put these up because it's easier than to draw the pictures. But so let me remind you again that two manifolds are actually geometric. So I mean, just beyond their topological description, they have geometric structures in the sense that, so for example, I mean, so they have geometries modeled on either the two-sphere or the Euclidean plane or the hyperbolic plane. So the two-sphere with its usual geometry where, geodesics are great circles, then there are only two manifolds modeled on that geometry. There's S2 itself and the projective plane, which is the quotient of the two-sphere by the antipodal map, which of course is an isometry in the spherical geometry. So that's familiar. And again, of course, equally familiar, the Euclidean geometry where straight lines are straight lines. And so the torus, of course, is a Euclidean manifold. It's the quotient of the Euclidean plane by Z cross Z's worth of Euclidean isometries. And then the generic geometry in dimension 2, of course, is the hyperbolic geometry. I guess we should call it the Bolyai geometry here, right? I mean, forget about Gauss and Lobachevsky, right? So the hyperbolic plane, where the model, the Poincaré disk model of the hyperbolic plane is just the open disk, geodesics being straight lines, being circles orthogonal to the boundary of the disk. And so again, a familiar example here. I mean, so most surfaces, are going to be have hyperbolic structures, and again, in the sense that they're the quotients of the hyperbolic plane by hyperbolic isometries. And so, to see this in a genus 2 surface, you sort of think of the genus 2 surface as an octagon with various sides identified. And so the octagon, you see, you get 8 corners of the octagon sort of meet at the point, and so you want an octagon with angle pi over 4, and so you can actually do that in the hyperbolic plane, and so you can tile the hyperbolic plane with these hyperbolic octagons and get the surface as a quotient of the hyperbolic plane by the appropriate group of isometries. And so you get this very nice classification of the geometries. Again, something very familiar, that which geometry applies is just a function of the Euler characteristic of the surface. So every two manifold M either has a geometry model on the sphere, the Euclidean plane, or the hyperbolic plane. In other words, it's the quotient of the appropriate space by a group of isometries acting sort of freely on the, and whether it's spherical, Euclidean, or hyperbolic depends on just whether the Euler characteristic of the surface is greater than 0, equal to 0, or less than 0. So again, that's very familiar, and this was known, of course, essentially in the 19th century, and so people wondered, what about three manifolds? What about three manifolds? I mean, maybe they have. So people wondered about this back in a long time ago. And there certainly are some examples. So again, let me just put up three examples here. Obviously, the 3 torus is an example of Euclidean 3 manifold. Just a natural generalization of the 2 torus. A more complicated example, which I'll sort of return to just in a second, perhaps in a slightly different guise, but the Poincare dodecahedral space. So this is not the description that Poincare gave, but this was a description that came sort of a few years later. If you take a regular dodecahedron and you identify opposite faces in the sort of most obvious way, namely you just twist through 2 pi over 10, just the smallest twist that makes the faces line up. You identify opposite faces, you find that this gives you a perfectly consistent identification of the boundary of this polyhedron, and you get a closed 3 manifold, and you find that the edges of the dodecahedron are identified in triples, and so at every edge you get 3 sort of corners, 3 dihedral sort of angles coming in, and so if you want to put a geometric structure on this, you need this dihedral angle to be 2 pi over 3, and that's actually just slightly more than the dihedral angle if you build the regular dodecahedron in Euclidean space. It just gives enough room to fit 120 of these things into the 3 sphere. And so, yeah.
You are standing in front of something.
Oh, I am. Oh, sorry. Oh, well, that's it might be just as well, actually. Okay, so there we are. So, yeah. So it turns out that you can actually, this manifold has a spherical structure. It comes from a tiling of the 3 sphere by 120 copies of this dodecahedron. And as I say, a classical example. And again, in the 30s, you see. So that's an example of a spherical manifold. And then one of the earliest examples of a hyperbolic manifold was very similar. Now you take a regular dodecahedron now, but now you identify opposite faces. There's essentially only one other way of identifying opposite faces, and now you do 3, times 2 pi over 10 twists, okay, to identify them as indicated. And again, you get a closed 3 manifold, and now the edges turn out to be identified, in 5s, and so you need to put a geometric structure in this. You'd need a dodecahedron whose dihedral angles are, sort of, what is it, 2 pi over 5, and you can actually do that in hyperbolic space. And so this was the example. This is a Cipher-Weber dodecahedral space. Built in 1933 and still works today. It's good German engineering, right? And so that's a classical example of a hyperbolic 3 manifold. Just very analogous to, taking an octagon in hyperbolic space with angles pi over 4. It's a 3-dimensional analog. Okay, so these are some examples of geometric 3 manifolds. And so people wondered, do all 3 manifolds have geometric structures? And so, again, it was realized fairly early on that this can't possibly be true because of the following. So, so here, so are all, well, so not all 3 manifolds have, so again, by geometric structure, I mean modeled on, you know, on the 3 constant curvature sort of metrics that we have, namely the 3-sphere, the Euclidean plane, and hyperbolic. Euclidean 3-space and hyperbolic 3-space. And I mean, a simple reason for that is that if M is geometric, that implies that its universal covering, you know, M tilde, well, it's going to either be, if it has a spherical structure, then it's going to be just a 3-sphere, of course, or in the other 2 geometries, it's just going to be homeomorphic to R3, and in particular, pi 2 of M would have to be 0. And so again, one of the first observations that was made historically, so e.g., you know, S2 cross S1 has no geometric structure in that sense. But you see, then you think, well, but maybe this is just because you're not allowing enough geometries, you see. So you could actually easily allow, so maybe you should allow some, I guess, what is the word, non-isotropic geometries that are homogeneous. They're the same at every point, but they're not the same in every direction. And so maybe you should allow S2 cross R as a geometry. I mean, so so this is clearly the quotient of this by, you know, by a group of isometries of the obvious geometry here, just the spherical geometry in this factor and the Euclidean geometry in this factor. And in fact, you can do this. It turns out that, again, I'm not going to say very much about this, but it turns out that there are 8, in other words, there are 5 additional geometries that you need to allow if you allow non-isotropic geometries in dimension 3. Well, so in this more general sense, I mean, there are the isotropic ones, and then there's, well, I don't know. I'm sort of, when I want to emphasize the geometry, I guess I'm sort of putting so maybe we should call this E1 or something. And then you have H2 plus E1. Then you have, I guess you have some weird things, SL2, the universal covering SL2R, 1, 2. Then you have a thing called nil, a thing called sol. Is that 8? 1, 2, 3, 4, 5, 6. Oh, okay, that's it. Anyway, but even then, you still, it's still the case that it's clear that not all 3 manifolds are geometric. So you still, if you take M1 connected sum M2, and let's say, let's say that pi 1 of Mi is non-trivial, then again, here's another homework exercise for you, that this implies that pi 2 of M is non-zero. So anyway, that's another. Yeah. And so again, I mean, something like this, a non-trivial connected sum couldn't possibly have possibly have a geometry based on either of these 3. And it turns out that actually it can't have a geometry based on any of the others either, except, well, there's this one case where the connected sum of 2 copies of RP3 is actually twofold covered by S2 cross S1. So that, Well, okay, so I mean, even in the generalized sense. Anyway, let me not get into that. But so anyway, the moral is that there are obvious, sort of pretty obvious obstructions to three manifolds having geometric structures, and so what is the picture? Well, so first of all, let me spend some time talking about, again, a case that was analyzed classically. So what's the kind of conjectured picture? Oh, so maybe so conjectured or maybe proved. I don't know. It doesn't. Okay, proved. Sort of picture of three manifolds. Okay, so the first case would be where the case you've got a closed three manifold, orientable, I'm assuming, and pi1 of m is finite. Okay, so what's supposed to be the situation there? Well, the universal covering is, see, it's a simply connected closed three manifold, so it's going to be homotopy equivalent to the three sphere, and so probably it is the three sphere, and probably the group is acting isometrically. So let's suppose you have, so the orientation, well, first of, oh yeah, okay, I'm only looking at orientable manifolds anyway, but, so the orientation preserving isometries of the three sphere is just SO4, right? The restrictions to the unit sphere of the orientation preserving orthogonal transformations of R4. And so if I have a finite, so if G is a subgroup of SO4 finite, and such that the action, its restriction, the action on S3, I'll stop putting these bars on, I'm sure, but anyway, is free, right? Then you get a spherical manifold. So then M mod G, right, is and so let me call it spherical. I mean, it has a spherical geometry, or sometimes called elliptic geometry. Oops, so this board's easier. All right. Okay. So that's the obvious source of three manifolds with finite fundamental group are just quotients of the three sphere by finite subgroups acting freely, finite subgroups of SO4 acting freely. And so the conjecture, of course, so I mean an important part of the geometrization conjecture is that every three manifold M with pi1 of M finite is spherical. So as I said, maybe that's proved. That's certainly a consequence of Perlman's work. So let me discuss these things in some detail, because again, this was classically done. So to some extent, this is a sort of historical account of the subject. But of course, an important example, are the lens spaces, the three-dimensional lens spaces, where you just, if you just think of R4 as the complex numbers cross the complex numbers, and you've got S3 sitting in here as the unit sphere, and you can let ZP, if you take P greater than or equal to 1, and Q to be relatively prime to P, then you can let ZP act on the three sphere isometrically. It acts as an element of SO4 just by, Z1, Z2 goes to, so I'm going to rotate one of these things through 2 pi over p, and then let's rotate the other direction through 2 pi q over p. So e to the 2 pi q. So this is a very simple but important class of examples of this type, and the quotient. So the quotient S3 mod ZP is the length space LPQ. Notice, of course, that a special case of this, if P is 2, then this is just the antipodal map. So this is just S3 multiplied by minus 1, so this is just RP3. So length spaces will feature in some of the subsequent lectures that I want to talk about in Dehn surgery. So let's mention them here. Anyway, let me say something about the more general finite subgroups of SO4 that act freely. Again, they were completely figured out a long time ago. So suppose, so the first thing to note is that if you think, so let's think of S3 as the unit quaternions, right? So S3, so R4, think of this as the quaternions, and so S3, the unit quaternions. And so S3 acts on itself, so S3, sort of acts orthogonally on itself by left multiplication and also by right multiplication. And so you actually, so you get a map. Well, and so you get a homomorphism phi from S3 cross S3 to SO4. So this is the double cover that Ron was talking about earlier this morning. So let me think of it in this way. I want to take two quaternions, Q1 and Q2, two unit quaternions, and that's going to define an orthogonal map from the 3-sphere to itself. So what I'm going to do is you multiply on the left by Q1 and on the right by Q2 inverse. So you just use left and right multiplication of the 3-sphere. And this is a twofold covering. The kernel of phi is just plus or minus 1, 1. So it's just Z2. So here's a source of, in fact, this is just another description of SO4, really. So you can, so really the task is to sort of figure out what, and phi is onto, I should say, yeah. So it's onto, oops. All right, wait. This is easier than taking the board down again, isn't it? Onto. Right, there we go. All right. I'm going to injure myself here. Okay. And so we have to, let's understand the finite subgroups of S3. Well, again, S3 is almost SO3. So again, you have this double cover, right? So let's call it rho from S3 SO3. So again, I want to think of that in terms of the unit quaternion. It's just sort of conjugation. If I take rho Q, then if I send X to QX, Q inverse, think of that as a transformation of S3 or an element of SO4. But you see, it fixes the real. So this fixes the real coordinate axis, and so it induces naturally an element of SO3, and so and again this is onto, this is the double cover. Kernel of rho is just plus or minus the identity, and so, and if you put all this together, then I mean you can just put this together in a commutative diagram like this. I mean we've got S3 cross S3 mapping to SO4. On the other hand, you get this projection to SO3 cross SO3, and so there's a natural map here that makes the diagram commute. And so the point is, so again, so SO4 is, I mean, it's almost SO3 cross SO3. And so if we want to understand, so if we have a finite subgroup, well, any subgroup, but let's say we take a finite subgroup of SO4 and we look at its image in SO3 cross SO3, then we can project. We have two projections. So I guess we have the projection here, pi onto SO3, just the two factors, and so we can look at the two projections of H. So we get two finite subgroups of SO3, H1 and H2. So HI, PI, H, subgroup of SO3. And of course, for every, this is a finite subgroup of SO3, and then of course we have the, so let's write HI star to be the corresponding finite subgroup of S3. So and so we get at our group G. If you think about it, this diagram, G is sort of, well, it's a subgroup of the image of these two, the direct product of these two finite subgroups of S3. Okay, so anyway, so the point is that what we need to understand then from this discussion, what we need to understand the first thing we need to understand are finite subgroups of SO3. So luckily that was done, so let me describe those. You haven't asked a question, Saul. Come on. Oh, yeah, right. Also trivial. All right, okay. All right, so the classical theorem of Klein, he figured out the finite subgroups. So the finite subgroups of SO3 are precisely, they're the cyclic groups, the dihedral groups. Well, let me look at a list. Okay, D2N. And then and then apart from those, there are just the symmetries of the regular solids. So then there's T, O, and I. So this is the symmetries of the tetrahedron. And this is the symmetries of the octahedron, well, cube slash octahedron, the two dual. The cube and the octahedron being dual, and similarly I, the dodecahedron, being dual to the icosahedron, and you have the symmetries of those. And so again, let me remind you that this is, these groups have presentations of the following form. This is they correspond to these these three triples: 2, 3, 3, 2, 3, 4, 2, 3, 5. And again, I mean, so T is actually just the alternating group A4, right? And O is the is S4, and I is A5. So this has order 12, 24, and 60. Anyway, so these are the well-known classification of the finite subgroups of SO3. And now, so somehow to understand the finite subgroups of SO4, we just have to sort of, we have these pairs of finite subgroups of SO3 sort of put together in some way which has to be sort of completely determined. But and I'm not going to go into the details, but the important point, the really important point here is that with this notation, one of these groups, HI, has to be cyclic, in fact. So you can have at most one of these more complicated groups appearing. So let me just quickly say why that is true. Well, I won't even prove it, but I mean, let me say something about it. Okay, so you can show. Is it? Let's see. Oh, so G SO4 finite, and again acting freely on S3. That's the important point. Then in fact, one of these subgroups of SO3, H1 say, is cyclic. And very roughly, the point is that all the other guys, the non-cyclic ones, all have even order, and so there'd be elements of order 2, and so you'd get so if not, H1 and H2 contain elements of order 2, and so you get you'd get a Z2 cross Z2 sitting in H1 cross H2, and then bit of fussing around, you show that in fact that you'd have to get a Z2 as a subgroup of G. But that's impossible because G is this finite subgroup of SO4 acting freely on the 3-sphere, and it's easy to show that the only Z2 that acts freely, the only element of order 2 that acts freely on the 3-sphere is just minus the identity, right? But the only Z2 in SO4 that acts freely on S3 is plus or minus identity. So that's just an elementary sort of computation. Or if you want to be sort of fancy about it, you say, well, if you have any group, a finite group that acts freely on any homology sphere, it would have to have, the cohomology would have to be periodic at period 4. And so you couldn't possibly have a Z2 cross Z2 in there because that doesn't have periodic cohomology. So, I mean, that's a sort of more general reason. Anyway, so that's why one of these factors, roughly why one of these factors has to be cyclic. And now it's just a matter of sort of putting everything together. And the final answer is a little bit more complicated. I mean, certainly you can have, for example, you could just take, for every one of these finite subgroups of SO3, you could take the corresponding twofold covering back in S3, and you could let that act on the right, say. Then you could take your favorite cyclic group, let that act on the left. Again, the cyclic group order would have to be relatively prime to the order of the guy you took on the right. Otherwise, it turns out for similar reasons you'd get you wouldn't be fixed point free. But so you can always take sort of direct products like that of a cyclic group with one of the sort of double covers of these guys. And it turns out there's one or two other things that can happen. But basically that's what happens. Anyway, let me just, because again, I mean, maybe, well, okay, so let me just state the theorem anyway, so roughly that, so again, let me say that for each of these guys, you know, you're going to get the corresponding double covers back in S3. So this is going to so anyway, corresponding to these, so you get the corresponding subgroups. I'm supposed to stop soon, right? Okay, you get the corresponding subgroups of S3. So this is of order 4n. So at the danger of a slight ambiguity of the notation, let me just call that anyway. So this is sort of the binary dihedral group, order 4n, and then you get these guys, the binary versions of they're sort of central extensions. I mean, there's, you know, that -1 is central. So you get the binary tetrahedral group. You get the binary octahedral group, and you get the binary icosahedral group. So these have orders, you know, 24, 48, and 120. And this guy, I mean, this guy is precisely the fundamental group of the Poincare homology sphere that I talked about, obtained by identifying the opposite faces of a dodecahedron. And so we see it come up in this analysis here. Anyway, so let me just state sort of Hop's theorem on the finite subgroups of SO4 that act freely on S3. So the finite subgroups of SO4 that act freely on S3 are, okay, so I mean, there's the ones that I've mentioned. I mean, you can take the trivial group, you can take these binary versions of the dihedral group, the tetrahedral, octahedral, icosahedral. There's a couple of weird things that come up. I mean, there are certain things, well anyway, there's things of the form. Let me not go into them, but I mean, it's something of order 2 to the k times n. They're closely related to these guys, but they're slightly different. And then there's also things, well, so D4n n odd is actually the same as D star 4n n odd. But in general, there are sort of some more of these. And then you also get things which are related to the binary tetrahedral groups, things with order 8 times 3 to the k. Well, I guess here k is just to be greater than or equal to 2. Here k is greater than or equal to 1. And again, I mean, T24 is just the T star, but then there are some others. And then finally, like I said, now you just so you take one of these guys, and then you take the direct product of any of these. With a cyclic group of coprime order. Okay, so that's the sort of story. These are precisely the spherical, they correspond precisely to the spherical 3 manifolds. And I'm sorry, what? Well, I mean, there you just, I mean, the direct product of two I mean, so cyclic groups are in here, right? Cyclic groups are, right. Because I took care to put the trivial group in part 1. So you can take a trivial group, direct product of any cyclic group, yeah. Then they correspond to the length spaces. Let me just finish by making an important, again, I'm sort of really following the history here. You see, Hopf classified these things, and then Cipher and Threlfall noticed this beautiful fact that because one of these summands here, you see, one of these factors, H1 star, for example, has to be cyclic. You see, so H1 you see, one of them has to be cyclic. And so you can conjugate that into the unit complex circle, okay? So so this is just the unit circle. This is in the complex numbers, which is sitting in the quaternions, and so. So think of this as this is the guy that's acting on the left, and so there's an S1 action. You can now just multiply by this S1. You see, so you get so left multiplication on S3. You see by S1. It's going to commute. It's going to commute with this left multiplication. Obviously, because but it's also going to commute with any right multiplication. See, so it's going to commute with the action of H1 star and with the action of H2 star, because that's on the right. And so, let me just finish with this. And so you see that the quotient then, you get this S1 action on the 3 sphere, which commutes with the action of the group. And so it induces an S1 action on the quotient, and so you're going to get a fixed point free S1 action on the quotient. That's the important observation of Cipher and Threlfall. So if M is S3 mod G, a spherical manifold, then there exists fixed point free S1 action on M. And this motivated Cipher then to define what are now called Cipher fiber spaces. And so let me just finish with that definition. And this is exactly how they arose. So a Cipher fiber space, which I'll almost always abbreviate to SFS, you see, so is it's a 3 manifold. Remember, everything's orientable and closed at this point. M, such that M is a disjoint union of circles, which are called fibers. It's a sort of singular circle bundle over a surface, really, is the way to think about it. Or in more modern language, it's a circle bundle over a 2-dimensional orbifold. But so it's a such that each. So this is Cipher's classical definition. Each fiber has a fibered solid torus neighborhood. By which we mean the obvious thing. You just take a solid torus and fiber it in a way that's sort of determined by 2 relatively prime integers, p and q. So you just think of taking a cylinder, d2 cross I, and now identify the 2 ends by a rotation through 2 pi q over p. Just twist and identify. So if P is greater than or equal to 1 and Q is relatively prime to P, so then you get a fibered, that's what I mean by a fibered solid torus. And that's the definition. And so notice that if P is greater than 1, then the core of the solid torus is an exceptional fiber. And all the others are called ordinary fibers. And so you get this, so that's the description of a Cipher fiber space anyway. And so, but if you then just identify each fiber to a point, then you get a surface, which is the so-called the base surface of the fibration. And again, it's really an orbifold because you have these finite number of sort of exceptional points, images of the exceptional fibers. And so I mean, I'm dealing with orientable three manifolds, and so if you have this fixed point free. I mean, if there's a fixed point free S1 action on M, then that implies that M is a Cipher fibered space with base surface orientable, and so all these spherical three manifolds, in fact, have this structure, and let me just finish off by saying that in the case of ZP, the lens spaces, then so the base surface is S2, and there are less than or equal to 2 exceptional fibers, and then in the sort of dihedral cases, the D star 4n or the D 2 to the k n, again the base surface is the 2 sphere, and you've got 3 exceptional fibers, and of course here you call the multiplicity, so multiplicity P, okay. So in an exceptional fiber, the nearby fibers sort of wrap around P times, in a neighborhood. So again, so here the multiplicities are 2, 2, and I guess you can guess, the T2, the T, what is it, 8, 3 to the Ks. Remember, that includes T star. And then the octahedral guys and the icosahedral guys. So again, the base surface is always S2, 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 3 exceptional fibers, and now the multiplicities are 2, 3, 3, 2, 3, 4, and 2, 3, 5. Okay, so that's a. I mean, there's more to the description of these manifolds than just these 3 numbers. Okay, but that's. There are some additional sort of numerical invariants that you need to do to describe the manifold uniquely, but anyway, that's the picture. Okay, so I guess I'll quit there, but that's definition of Cipher fiber spaces. So what I'll do next time is just spend perhaps the first part of the lecture talking more about 3 manifolds. We just have to discuss a little bit, I won't say very much, the hyperbolic case. So here's the case when pi1 is finite. What happens when pi1 is infinite? Well, you get some Euclidean manifolds. It turns out there aren't too many of those. You get an awful lot of hyperbolic manifolds, but again, not all manifolds with infinite fundamental group, which are irreducible even, have geometric structures modeled on E3 or H3. There's an additional obstruction which comes from the existence of tori, and so I'll just mention that and describe what's known about tori, and then we'll be able to state the geometrization conjecture and move on to Dehn surgery. Okay, so thank you.